Okay, so a little Missy here is kind of hogging the space right in front of the camera. But yes, I'm here too. Welcome to Math with Doug. Welcome to Math with Dog. The dog likes algebra, so she's going to enjoy this lesson. But it's time for her to lie down and get comfortable. That's right. Big squashy armchair just for you. Lucky dog. Okay, and this is Olympique Marseille. That is the jersey of today, a rather beautiful, stylish French soccer league jersey. And we are still on pre-algebra. And we have a bunch of phrases which are mathy, but they're in the English language. One of the things we're going to do today is practice translating between English and math, which is a skill you have to have when you're doing math, very much involved in word problems and learning situations. And we are still getting into all the background material that comes together to make us able to understand algebra. And the very first thing we're going to talk about is the variable. So a variable, what's a variable? It's a letter that we use to represent a number that we don't know yet, or a number that might keep changing. So a very common variable is x, but we can use any letter we want for a variable. So other commonly chosen ones are y and a and b and m and n and p and q. Why do we need more than one letter? Why can't we just use x? Well, because sometimes in algebra we have more than one variable involved at a time. So you have to be able to have more than one letter that's being used as a variable. As for why we have all these particular ones that are used more often than others, that's just a matter of, giving us some variety. The truth is that an expression like 2x can also be expressed as 2a. So long as we realize, okay, well, in this case we're using x for a variable, but over here we're using a for our variable. That's the sort of thing that happens. Let's get into it though. Let's get into this translation, because that's really why I'm mentioning variables, because when we translate between this English and the math, we're going to have to use a variable to express a number, because in this sentences that we have here, the number is a number we don't know yet. We don't know what it is, so we can't write down the number. We have to write down something in place of the number, and that's the variable. Okay, I'm going to erase this collection of letters here and use this space to write the math translations of these. Now, why did I put blanks, lines where something's missing? Because I know what students are like. If I hadn't done this, if I had written in all the missing words, then students would already be finished doing all 5 of these questions, and I'd be standing here talking to myself. So that's my ploy, to make the students wait a little bit until I get around to asking the questions. So the first one, twice the sum of a number and 7. So the word that's missing is the word 7. Okay, so we have to know what the words mean, but of course a lot of them are quite easy to use, and you tend to see the same things over and over again. So twice, commonly already understood word in the English language, that means that we are doubling something, that something is being multiplied by 2. Twice the sum, the sum is what you get when you add things together, a total of a number. That's what we're looking for, a number. We're going to use a variable to represent a number. So let's say we start with x, the most commonly used variable. X can be the number, but I'm not finished, because we don't just have a number in this sentence. We have twice the sum of a number and 7. The number and 7, meaning x plus 7, there, x plus 7 therefore would represent the sum of a number and 7, but I have to multiply that by 2. So therefore I'd want to do this. Twice the sum of a number, x and 7. So I have done my best to translate between English and math, and I end up with this algebraic expression which can then be worked with our math skills. Here's something that's missing. I have to remember what's missing. 5 plus 3 times the number. 5 plus 3 times a number. Okay, so this time let's use y as a variable. So 3 times a number, y will represent a number, and then 3 times a number would be 3y. But then we're adding 5 to that. It is 5 plus 3 times the number, so 5 plus 3y. We're able to translate between English and math. This actually gets easier and easier with a bit of practice, so it's a good idea to practice it a lot. 15 minus what's missing that time? Twice. Oh, it's that word twice again. 15 minus twice a number. Okay, so 15 minus 15 minus twice a number. Okay, 2 times the letter I'm going to use my variable. Let's use a this time. Twice a number would be 2a. 15 minus 2a. Interesting. And you see how the wording helps us to figure out the correct algebraic expression to make. I wanted to use the bracket in this first one because I saw the sum of a number and 7, but that's going to be multiplied by 2 after. The bracket sort of makes us do it in a certain order. Let's go back and use x for the last 2 that I have here. My dough is 2 inches higher. Oh, this is very situational. This is very word problem-y. My dough is 2 inches higher than it was this morning. Okay, so I never said the phrase a number here. So I have to do a little bit more translating. But the height that my dough was this morning, perhaps not long after I mixed it with yeast, etc., that can be my variable. That can be, because it varies. The height of the dough would vary with time. Makes sense. So the height that the dough was reaching this morning can be x, and my dough is now 2 inches higher than that. So if x is the height the dough was this morning, now it's 2 inches higher, so that is x plus 2. I didn't use the word plus in the sentence, but I was still able to realize when I needed to add. I didn't use the phrase a number, but I was still able to figure out what it was I wanted to make my variable equal to. I'm getting better at this. Okay, then this last one that I have here, I have another one that I just didn't have space to write down. But the last one that's written here, I made 4 times more ice cream in cones in June than in April. That kind of makes sense. So 4 is the word that's missing in this one. Yeah, it makes sense that, well, depending on which hemisphere you live in, it makes sense that you might make more ice cream cones in June than in April. The weather will be warmer. We're kind of getting to that time of year, so that's why I was thinking of that, maybe this example. 4 times more ice cream cones in June than in April, so therefore the amount of ice cream cones I made in April, I don't know what that is. It's a number, but I don't know what it is yet. So how about I use a variable to express it? I'll use x. X is the amount of ice cream cones I made in April, and in June I made 4 times that amount. Oh, so 4x, therefore, would represent the number of ice cream cones I made in June. Makes sense, and it's fun. This is fun. Believe me, it's fun. I want you to understand that I really think this is fun. How am I doing for time? Okay, I'm going to erase all of these and put my last one, which is a fairly long one, and then we'll move on to something else. The last one, this is sort of like a restaurant situation. So let me write it out. The number of diners quadrupled at lunchtime. Not finished, but then 20 of them left. Oh, okay, but then 20 of them left. So there's a lot here. We had a certain number of diners in the restaurant, but then it became lunchtime and suddenly it quadrupled. So let's say that the number of diners we had before lunchtime was X. But then it quadrupled. So that means I'm multiplying it by 4. But then after a while, 20 of them left. Okay. So the number of diners I have at the end of all of this would be 4x minus 20 if the number I had before lunchtime was x. It makes sense. I'm translating from English to math, and it is kind of fun once you get the hang of it. And it becomes easier and easier with practice because there are only so many ways that we can write out these sort of situations in English. So you tend to see the same phrases and the same words being used quite often. And the words become more and more useful in order to correctly create an algebraic expression. Okay, so that was fun. And I have finished the whole first page of my lesson plan, which is, it didn't take long to finish that page because there are a lot of words on it. Okay, second page. Oh, evaluating expression. Now this is going to get really fun. We're getting into the nuts and bolts of algebra, the sort of thing that happens again and again and again, and that will always be fun. So, an expression. Well, there's an expression. We already have one sitting there. Should I use that one? Should I suddenly change my lesson plan? Yes, I will. Okay, I'm going to evaluate this expression. What does that mean? It means that, well, depending on what number x actually is, what would be the answer if I replace x with a number? So let's try a few numbers. Let's say x equals 10. Well, if x is 10, then I can replace x with a 10, and then I can simplify. Can't really simplify this because I have 4x and minus 20, and I can't really combine them because they're not similar terms. This one has an x and that one doesn't. But now that I've replaced x with a 10, everything's numbers. And I can just follow my order of operations and simplify. 4 times 10 is 40. And then 40 minus 20 is equal to 20. So if x is equal to 10, then 4x minus 20 ends up being equal to 20. Let's try a different value for x. What if x is equal to 12? I'll write x equals 10 in brackets above this one, and then I'll do x equals 12 here. Okay, therefore, I still have 4x minus 20. And I really like to write my expression down without taking away the x and replacing it with a number, because I like to show at the beginning of my calculations what expression did I start with. Then I plug in the number. Okay, so the x is being replaced this time with a 12. So it's 4 times 12 minus 20. And the order of operations tells me to multiply before I subtract. 4 times 12 is equal to 48. 48 minus 20 I can now do, and my answer is 28. It's fun. And how many times can I do this? I can do it over and over and over again, just using different values for x. And that's what I mean when I say sometimes x is a number we don't know what it is yet, but sometimes x is a number that might change. So this expression, 4x minus 20, it's almost like a little machine that we plug raw materials in, and then it produces something. So if I plug in the raw material of 12, the machine produces a 28. But when I plug in the raw material of 10 instead, the machine produces a 20. And that is fun. So we can do this as many times as we want with each expression. Let me go back to, nearly out of chalk. Let me get a new piece of chalk. And let me go back to my lesson plan and put in the expression that I intended to start with. So this one is going to be 3x plus 6. And in fact, I'll write it 3 times because I'm going to plug in 3 different values for x. Okay, so I'll put those in brackets again. I may as well just keep on using the same style. So the x's that I decided to evaluate this expression for are x equals 3, x equals 4, x equals 2. And here I go, my machine is warming up and I can start using it. Okay, so if x is equal to 3, 3x plus 6 becomes 3 times 3 plus 6. Notice how we are substituting a number for x, which means the x is not there anymore. So we do not want to put the 3 in there and keep the x. That would turn this expression into something else. This expression is 3 times 3 plus 6 when x equals 3. And 3 times 3, of course, is 9. And 9 plus 6 is equal to 15. This sort of rolls downhill once you get going. Okay, but if x is equal to 4, we have 3 times 4 plus 6. 3 times 4 is equal to 12. 12 plus 6 is 18. Notice how this stuff that we've been practicing with the order of operations comes in so handy to make sure that we can get through this easily without making a mistake. If x is equal to 2, 3 times 2 plus 6 is equal to 6 plus 6, which is equal to 12. Again, I could do this so many times, I could do it forever, couldn't I? But I'm going to change the expression, and then we'll do a few more examples. This is something I want to do a lot of examples of. And this thing we're doing, where we have an algebraic expression, but we have a need to plug in a number, substitute a number for the variable, and simplify and find out what answer it gives, is something that will happen again and again and again for the rest of the time that you ever do algebra, and in fact for the rest of the time that you ever do most types of math from now on. So it's a good thing to practice and be good at. My next expression is 4x minus 3. It's not always involving a plus sign. What if we have 4x minus 3? And again, I will do this 3 times. And I'll replace x with 3 different numbers. Wait. I want to make sure that students are comfortable with this idea. And it doesn't always have to be x. We can use any variable for our unknown number, so I'm going to go for that a. One of the most common choices of math teachers everywhere. For a minus 3. It works the same way. We're just using a as the variable instead of x as the variable. Everything else is the same. Oh, but we're subtracting now. So that's a little different, but we know how to subtract, so it's not different. How about if x is equal to 8 or 10 or 12? Not x. If a is equal to 8, or if a is equal to 10, or if a is equal to 12, we want to evaluate this expression. Does it have to be 3 times? No. It could be 27 times or just 1 time. But 3 times gives us a bit of practice. Okay, so if a is equal to 8, we have 4 times 8 minus 3. 4 times 8 is 32, so we have 32 minus 3. 32 minus 3 is equal to 29. If a is equal to 10, 4 times 10 minus 3, which is 40 minus 3, which is 37. And if a is equal to 12, 4 times 12 minus 3, which is 48 minus 3, which is 45. Fun. I find this fun. And if I'm still finding it fun after all the years that I've been doing it, well, then I know the students must be finding it fun as well. Well, what else can happen? I'm going to juggle things around. So I'm going to do another one. I guess I'll change the variable again. How about m? I'll use m. Over the years, I've known teachers who really liked m and n for variables, and then other teachers who never used m and n. So people have their personal preferences and how they like to do this. And the algebraic expression is not very complicated, not yet. We'll see what happens as we progress through this lesson. How about if my expression is 2x minus 6? I'm back to x. No, I said I was going to use m. I'm using m. 2m minus 6. Do that 3 times as well. Make sure it all fits in my rectangle. And x, for x, I'm going to use 4. But I'm also going to, not x. I have to remember my own variables. M is equal to 4, or m equals 1. Something interesting is going to happen here. Or m is equal to, I'll save that one. Do that one as a surprise. If m equals 4, then 2m minus 6 is 2 times 4 minus 6, which is 8 minus 6, which is equal to 2. Huh. We got a smallish answer this time. Why? Because I'm doubling a smallish number like 4, and then I'm subtracting a biggish number like 6 from it. So, I subtracted my way almost down to 0, but what's the matter if I go all the way down to 0 or past 0? Is there a problem? No. We're about to find out. If m is equal to 1, then I have 2 times 1 minus 6, but 2 times 1 is 2. I have 2 minus 6. Uh-oh, a couple of weeks ago we wouldn't have been able to deal with this. What's this? 2 minus 6. 6 is bigger than 2. We know how to use integers. So when we are subtracting a larger integer from a small one, we end up doing 6 minus 2 is equal to 4, but the answer is got the sign of the smaller one. I'm applying one of the rules of adding and subtracting integers, but my wording is a little clumsy. But we were able to get an answer. It's a negative answer. Is this a problem? No. And in fact, this will happen quite often in algebra. And that's one of the reasons that we have to learn about integers before we get involved deeply into algebra, because situations like this will happen and it doesn't stop us from being able to do the math. What am I doing for time? Okay, so that's why I wanted to save this one as a surprise. I am going to make m equal to negative 5. Aha, so we can plug in a negative value to substitute for our variable. Yes, we can. Why not? So therefore we have 2 times negative 5 minus 6. And we can do this. 2 times negative 5. Positive times a negative gives a negative. 2 times 5 is 10, so I have negative 10. But I still have to subtract, negative 10 minus 6. So when I'm doing negative 10 minus 6, I'm adding the 10 and the 6 and I'm getting 16, but the answer has to be negative. So the negatives didn't stop us, did they? That's good. So we're adding our skills of adding, subtracting, and multiplying integers, and it just seamlessly allows us to continue with this evaluating expressions thing without there being a problem, because we know how to deal with integers. Now I have, let's see, what do I have here? Well, do you always have an expression where you have something like 2m minus 6 or 3x plus 6 or 4x minus 3? No. You can have any sort of algebraic expression. Things can get more complicated without, if you'll forgive me, becoming too complicated. Because we already know all the rules, so we're going to be able to keep doing this even if I make the algebraic expressions more complicated. Like, for instance, what if my algebraic expression has more than one variable being used? So let's do an example of that. 2a plus 3b. Okay, the problem here is I can't just say if a equals and give you a number. I have to provide a value for a and a value for b. So what I'll do, how will I write this? I'll just say a equals 2, b equals 3. Okay, so if a is equal to 2 and b is equal to 3, I'm doing the same thing. I'm substituting this a for that 2, so I have 2 times 2. But I'm not putting a 2 here because this is a b, and b is not equal to 2, b is equal to 3. So I have 3 times 3. And now I can simplify. 2 times 2 is 4, and 3 times 3 is 9, and 4 plus 9 is 13. I'm just following the order of operations. Let's do it again, but with different choices of values for a and b. How about if a is 5 and b is 1? A equals 5, b equals 1. Therefore, I have 2 times 5 plus 3 times 1. No problem. 2 times 5 is 10, 3 times 1 is 3, 10 plus 3 is equal to 13. Hey, I got the same answer. That's just a coincidence. Okay, what if I do it a third time? 2a plus 3b. But this time my a is equal to 10 and my b is equal to 20. No problem. 2 times a becomes 2 times 10, plus 3 times b becomes 3 times 20. 2 times 10 is equal to 20. 3 times 20 is equal to 60. I ended up with 80. Not 13. Anything can happen. I could make up enough questions for a 24-hour lesson with just this one algebraic expression of 2a plus 3b, really, because all the different combinations of numbers that I could substitute as my a and my b gives me a new question every time. Again, it feels like that machine. I'm getting good at using this particular machine, but what's even more important is I'm getting good at using any machine. any algebraic expression machine, I can do this stuff too, because it really isn't getting more complicated. As I make the question more complicated, the answers are not getting more complicated. And that is because we have power. We have power of knowing how to evaluate expressions. Let's do one more. I'm going to use the same A and the same B for 3 examples, but this time what I'm going to do to make new questions is I'm going to change the expression. So I'm erasing all this. I'm still going to have an expression with 2 different variables, which will be A and B, but I'm going to use the expression 3A minus B instead. Okay, let's substitute. If A is 2, this becomes 3 times 2. Minus B, B is 3, it's just minus 3. 3 times 2 is 6, and 6 minus 3 is equal to 3. I have the answer, it's 3. If A is 5 and B is 1, 3 times 5 minus 1. 3 times 5 is equal to 15, and 15 minus 1 is equal to 14. It works. If A is 10 and B is 20, 3 times 10 minus 20. 3 times 10 is equal to 30. 30 minus 20 is equal to 10. I have my answer. Let's do a 4th one, because none of my answers ended up being negative. Can the answer end up being negative? Yes, that already happened in a previous example. How about if I have A equals 2 and B equals 8? What's going to happen now? 3 times 2 minus 8 is 6 minus 8, which is equal to negative 2. Still works. I don't have to have negative answer. I don't have to have positive answers for this to work, because I can handle integers. What if I plug in? I'll do a 5th one. If A equals negative 4 and B equals negative 7, 3A minus B becomes 3 times negative 4 minus, negative 7. Have to be careful. Lots of negative signs. Things can get confusing, and that's where you need to just slow down. I am subtracting B minus B, but my B is negative, so I am subtracting a negative. As long as I'm careful, I can still do it, because I know all the algebra skills and all of the integer skills I need to do this. 3 times negative 4 is negative 12. Positive times a negative, negative answer. Minus negative 7 is the same as plus 7. Negative 12 plus 7. It's like negative 12 on the thermometer, but it gets 7 degrees warmer. It's still not going to be a positive answer. Negative 12 plus 7 is equal to negative 5. I have my answer. I can handle this no matter what's in the algebraic expression, and no matter what values I'm plugging into the algebraic expression. That is a feeling of power. And my 2nd page is now done, and I'm almost at the halfway point. Now we will break away from that sort of thing for a while, and then we will come back to it, because I want to talk about exponents for a bit. Now, we've seen exponents before, so they're not new. And this is one of the interesting little puzzles when you're trying to teach math, is you get to something like exponents, which at first students never deal with them, don't even know what they are. And then eventually you want to start teaching the students things like the geometry of a circle, and they have to do pi r squared, which the students who are doing this lesson have done. But pi r squared, the radius is squared, that's an exponent. So what do you do? Do you always have to teach exponents first before you start teaching geometry? It doesn't really work out that way. With all these different topics in math, sometimes you will realize that there's such a thing as an exponent while you're doing your geometry and learning things like area of a circle equals pi r squared. You'll learn how to deal with that. And then later on you get to a lesson like this one where we decide, okay, now we're going to go into some more detail about exponents. We're going to exercise our exponent muscles for a bit. So, an exponent like 2 squared, or 2 cubed, or 2 to the power of 4, or 2 to the power of 5. And of course it can go on and on, so I won't go on and on. 2 squared simply means I'm multiplying 2 by itself, and there will be a total of 2 2's. Kind of took a long time to say that. It means 2 times 2. And 2 times 2 is equal to 4. 4 is a power of 2, because I can bring 2 up to the power 2, and 4 is my answer. But whatever I get as my answer when I bring 2 to the power of 3 is also going to be a power of 2. we get used to this terminology, and we get used to these numbers. We see them a lot and we start to memorize the answers. A lot of students see 2 cubed and they know immediately what it's going to be without actually doing some multiplication. It's 2 times itself, total of 3 2's. Okay, 2 times 2 times 2, therefore. 2 cubed is equal to 2 times 2 times 2. And 2 times 2 is 4 times another 2 is equal to 8. 8 is a power of 2. 2 to the 4, I'm going to run out of room. So I'll just go lower. 2 times 2 times 2 times 2. There are 4 2's. That's the 4. 2 times 2 is 4, times another 2 is equal to 8, times another 2 is equal to 16. It turns out that 16 is also a power of 2. 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16. What's going to happen next? And we start playing around with the patterns we're seeing. Wait, 4 doubles to become 8, which then doubles to become 16. And if I double 16, I'd get 32, right? Does that mean 2 to the power of 5 is equal to 32? 2 times 2 times 2 times 2 times 2. 2 times 2 is equal to 4, times another 2 is equal to 8, times another 2 is equal to 16, times another 2 is equal to 32. So the answer is yes. Notice there are 4 multiplication symbols in this. That's a 5. There are 5 2's. So in order to show 5 2's being multiplied, you need to show 4 multiplication symbols. When you look at this number, that's telling you how many times the base. The 2 is a base. It's called a base in this expression. That's how many times the base is multiplied by itself. 4 multiplications are what's necessary to multiply 5 2's all by each other, and we end up 32. And so we can look at the pattern. 4, 8, 16, 32. The next one must be 64. That means 2 to the 5 must be equal to 64. And if we can multiply 64 by 2 in our heads quickly and get 128, that means 2 to the power of 7 must be 128. And it goes on and on. But of course, 2 isn't always your base. So what if we have other bases, like 3? Let's do some more. We can handle this because we already know how to multiply. So therefore, we know how to apply exponents. So I just gave 3 examples with 3. How about 3 squared, 3 cubed, and 3 to the 4? 3 to the power of 4, or 3 to the 4, that's how I say it very often. For short, 3 to the power of 4 sounds like the correct way to say it. 3 squared is equal to 3 times 3, which is equal to 9. 3 cubed is equal to 3 times 3 times another 3, which is equal to 9 times 3, which is 27. That 9, it's not doubling anymore. 9 doesn't double to give 27. 9 triples to give 27. That's interesting. Triples. So therefore, if I triple 27, everyone knows that 3 times 27 is equal to 81, right? Use your calculator if you need. Okay, so I'm going to get 81. That's my prediction. But how do I get that? I do 3 times 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3. 27 times 3 equals 81. Yes. 9 times 9 is equal to 81. 3 times 3 is equal to 9. 3 times 3 is equal... Ooh. The patterns are just fun to see. This is one of those types of math that there should be a little puzzle book. I'm always saying this, aren't I? A little puzzle book that you buy in the train station at the airport, or the at the bookstore at the train station, or in the airport, or in a bus station, or any bookstore. And that's full of puzzles where they're all exponents, and you're multiplying them out, and you're finding out what powers result in those exponents. And then, of course, you have your easy level in the early pages, and it gradually gets to the gigantic number level at the pages near the end, and it's just fun, it's stimulating, it's interesting. But we start to see the same values happening over and over again, and we start to remember the answers. So you start feeling confident with things like the fact that 3 cubed is equal to 27. Useful. It will be useful. Now, where did we see some of this recently? Yes, I was mentioning that area of a circle formula. Let's erase these powers, these exponents. There are more. I'm going to get into some more. But the area of a circle is equal to pi r squared. We square the radius to get the area of a circle. And that is an exponent. And that's why I was mentioning when we were doing this geometry, I was mentioning the order of operations. The e for exponent happens before the m for multiply. So I want to square my radius first and then multiply by pi afterwards. I'm not doing a geometry problem now though. What else did we see? We saw the volume of a cylinder was equal to pi r squared times h. Pi r squared, which is the area of the circle that is at the base of the cylinder, times h, which is the length of the tube of the cylinder. And there you are with an r squared again, another exponent. Yes, we have seen this before. And then you have the volume of a sphere, which is 4/3 pi r cubed. Yeah, they're not always squared. You will see exponents in other types of math that are not always 2's. Again, that's just a reminder that we have seen this before, and that there is always overlap between these different branches of mathematics. But since they're all fun, we don't mind when there's overlap. How about 4 squared, 4 cubed? Ooh, 4 to the 4. These are getting big. These numbers are getting big. How about 5 squared, 5 cubed, 5 to the power of 4, even 5 to the power of 5. Can I do that? We'll see. Can I do these without having to reach for the calculator every time? 4 squared, that's 4 times 4. No problem, that's 16. We knew that. 4 cubed, that's 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is equal to 64. 4 to the 4. 4 to the power of 4. See, as you see, we get larger bases when combined with larger exponents give us larger answers. But is this a problem? No, it's not a problem. We do have a calculator when we need it. 4 times 4 is 16, times 4 is equal to 64. 64 times another 4 is 256, isn't it? Yes, it is. So yes, do it in your head when you can, but whenever you get into the bigger numbers and you're not sure, learn your lesson the way Doug has learned his lesson. And 4 times 4 times 4 times 4 equals 256. It's okay, I got it. I'll do these 5s, and then I want to get back into the calculator. Do some exponents on the calculator. 5 squared, that's 5 times 5, which is equal to 25. Easy one. 5 cubed, 5 times 5 times 5, which is 25 times another 5. 125. Okay, the answer is getting bigger very rapidly. Bigger base, bigger exponent. 5 times 5 times 5 times 5. 25 times 5 is 125 times another 5 is 625. 5 to the power of 5. 5 times 5 is 25, times 5 is 125, times 5 is 625, times 5 times 625. 5 times 600 would be 3,000. 5 times 25 is 125. So this must be 3,125. But if I'm not sure, I'll check in the calculator, and there's more than one way of doing this in the calculator, which is what I want to get to next anyway. First, I'm rubbing all the chalk dust off from the calculator because it's just embarrassing how dusty it gets. And that means I have to press clear button because all sorts of stuff was happening in there. Okay, 5 to the power of 5. 5, let me see, am I showing this at all? 5 times 5 times 5 times 5 times 5 equals 3,125. But I also have this y to the x button, there it is, on this calculator. So all calculators have a way of doing this. But all scientific calculators have ways of doing the exponents. But this one has y to the power of x. I've seen it when it's called x to the power of y. I've seen it when all it looked like was one of these. That is a symbol that can be used to mean, oh, there's an exponent. So you have to learn the buttons to go with your particular calculator. But with this y to the x button, I'm doing 5, then I'm pressing y to the x, and then I'm putting another 5. So I'm telling it that my base is a 5. I want to bring it to an exponent, and it says, what exponent do you want? And the exponent I want is another 5. 5, then y to the x, and then 5 equals 3,125. No problem. So play around with the exponent buttons on your calculator. Learn how they work. They're fun to use. And that is a way of practicing doing this, because these bases being brought up to an exponent is part of algebra. It's going to happen sometimes in algebra. What might that look like? Can a variable have an exponent? Let's think about that. All of these were bases that were numbers, but were being brought to exponents. But what if base is not a number? What if the base is a variable, like an x? So like x squared. Can I do this? Yes. We saw area is equal to pi r squared. R is a variable. It's a variable. We choose the letter r when we want it to denote the length of a radius. So r squared, not very different from x squared. So what are some other examples? We could have a cubed. No problem. We can have b to the power of 4. We can have a to the power of 4. We can have x to the power of 3. We can have a to the power of 17. Bringing things to a power results in larger and larger answers. So when the powers get really large, the numbers can get very big and hard to write down. But then we can also have something like this. X cubed minus 2. Look familiar? Yes, it does, because this is an algebraic expression, and we were evaluating expressions not too long ago. Can you still evaluate an algebraic expression when it has exponents involved? Yes. How much time do I have left? I'm on to my fourth and last page of my lesson plan. So, we will try evaluating some algebraic expressions with exponents, but first, I want to talk a little bit more about something sitting right here to talk about, which is that we cannot combine these because they're not like terms. This is an x and it's an x cubed. This is just a 2. It's a constant term. It doesn't have a variable. They are not like terms. It's like apples and oranges. I have x cubed apples and I have 2 oranges. I can't really combine them by subtracting. So I just keep them, I consider this already simplified. I keep them separate like that. But what if I had more than one, and what if I had a longer algebraic expression with a whole bunch of terms? And what if there was more than one term that has x cubed? What if there was more than one constant term that had a number with no variable? Well, let's find out what if. Let's do it. And we'll get back to evaluating expressions with exponents soon. Here's one. I don't want to start with too big a one. How about 2x squared plus 3x plus 5x squared minus x. So we have this term that has x squared. And we have this other term that has x squared. And we should be able to combine them because it's like apples and apples. And then we have this term that has an x. We can't combine it with these other two because that's like an orange. Apples, no, orange. Oh, there's more apples. I can combine my apples. I could say I have 2 apples plus 5 apples, I have 7 apples. Which in math, cooler sounding math languages, I have 2x squareds, but I have to add 5 other x squareds. So I have 7x squareds. Therefore I have 7x squared. It works. But I'm not finished, because what about the 3x and the minus x? Well, when you get to have an algebraic expression with more terms, it could start to be more difficult to keep track of them all. So one thing that's useful is to cross out these two because we use them and combine them into 7x squared. And now we look at what's left. We have a 3x, but we also are subtracting an x. 3x minus x will give us 2x. 3 oranges minus an orange gives us 2 oranges. And we're done. We now have an algebraic expression with just 2 terms in it, but we do not want to try to combine them because they are not like terms. We have the apple and orange thing, we cannot combine them. So 7x squared plus 2x is my answer. As far as I know, unless someone tells me, hey, let's make x equal to, and gives me a number, then I would evaluate, right? But that's for later. We're combining like terms, and we can do that with addition and subtraction. We take the ones that are alike, and if they're both positive, we are combining them with addition. We take the ones that are alike, and if one's positive and the other one is negative, or if you will, if one of them is being added and the other one's subtracted, then we combine them using our adding and subtracting skills, which are skills we already have. Let's do another one. I'll switch to a different variable. Let's use y. I haven't used y very much. How about 3y minus 6y cubed plus 2y squared plus 10y cubed minus y. Whew. Apples, oranges, and some other fruit. Because we have y, there are two of those. And we have y cubed, there are two of those. So there's only one with y squared. That one's that lonely 2y squared is not going to be able to combine with anything else because there are no other like terms. There are no other terms that have y squared. But I'm not going to let that bother me. I'm going to start with minus 6y cubed plus 10y cubed. Ooh. So I'm using my adding integer skills. Negative 6 plus 10 is going to give me positive 4y cubed. And therefore I've used these. But I also have 3y. That's a positive 3y because there's no minus sign before it. So that means it must be positive 3y, but I'm subtracting a y. 3y minus y is 2y. I'm writing plus 2y. And then, I still have that 2y squared. I'm going to cross these out, then it's really clear. Okay, I only have one 2y squared. I only have one term with y squared. So I have plus 2y squared. Now often, you'll see a student rewrite this in descending powers of y, which sometimes there's a reason to do it, sometimes you have to do it, sometimes the question tells you to do it, and other times you don't have to do it. So I'm just going to rewrite it because I can, which means I'm putting y cubed first, and then I'm putting the y squared term second, and then I'm putting the y term last. These are both correct. They both mean the same thing. If we want to go back to our apples and oranges, we need another fruit. Watermelons. Yeah, why would I mention watermelons? Because this week's fizzy water is watermelon flavor. That's good. Okay. We had minus 6 apples plus 10 apples. We got positive 4 apples. And we had positive 3 oranges minus 1 orange, and that gave us 2 oranges. And then we had 2 watermelons. So we still have 2 watermelons. So I can say 4 apples plus 2 watermelons plus 2 oranges. Doesn't really matter the order that I put them in, but it looks kind of tidy, doesn't it? Sometimes there's a reason, though, to have descending powers of your variable, and it could be possible that you would want ascending powers of your variable, which, again, that means it's another correct answer, isn't it? I can write this as 2y plus 2y squared plus 2y, not plus 2, plus 4y cubed. Okay, so now I put the watermelons. Yeah, put oranges, then watermelons, then apples. I think y and x are better than the fruit because they're shorter to say and they're shorter to write down. Maybe I should just stop talking about fruit and talk about y. Y cubed, y squared. What's the matter with that? We know the lingo, we know how to talk about this math, so we use our math language skills to talk about our math. Keep on getting back and forth between math and the English language. It's kind of interesting. There's a theme that doesn't go away. Let's do another one. Time for a trick question. Of course, the worst thing you can do when you want to ask someone a trick question is to tell them ahead of time that it's going to be a trick question, but I'm doing that. I have 3x cubed plus 5x plus 6. Can't simplify it. There are no like terms. This has x cubed, this just has x, and this doesn't have a variable at all. It's a constant term, so trick question. Simplify this. Can't. I could evaluate it if you told me that x is equal to 2 or something like that, I could, but I'm not doing that right now. I'm checking how much time I have left because I do want to do some more evaluating. But not this one. So I was just there, just pointing out that sometimes you're going to be simplifying things. You're going to get to a line in your math where you think, oh, I should probably combine like terms. And then realize, hey, there are no like terms. So I'm done. That happened. Okay, let's do a long one. 4x squared plus 3a squared. I'm going to pick up my clipboard because I don't have to walk back and forth too long because there are, how many terms? Eight terms in this one. See, it gets more complicated, but it doesn't, because the skills we're applying make it just keep on being easy and doable, even if I write a really long expression, which is what I'm doing. So I have plus 6b squared minus x squared plus 2a squared. Am I going to run out of room in my little rectangle window? Maybe not. Minus 8 minus 4b squared. I'm getting near the end of... No, there's still room. Plus 2. Okay, I better stop there. So I have 8 terms in this algebraic expression, and I want to combine like terms, and it sounds scary, except it's not scary. Because I can start with anything I want. I'll start with the x squareds, because the first thing I got to reading left to right is a term where the variable is x squared. Is there any other term with an x squared? Yes, there is. It's right here. So I'm crossing. It's the only two that there are only 2 terms here that have x squared. So it's 4x squared minus x squared. That's going to give me 3x squared, and I've already crossed them both out. And now I'm getting to my a squareds. I have plus 3a squared plus another 2a squared, and that's the only 2a squareds. Plus 3 plus 2, that's plus 5a squared, and I'm going to cross those out. Okay, b squareds, I have plus 6b squared minus 4b squared. Those combine to give me plus 2b squared. It's the only b squareds, so crossing them out. And all I have left is this minus 8 and that plus 2. Constant terms, minus 8 plus 2 combines to give minus 6. I am applying my adding and subtracting integers skills while doing this, simplifying a very long algebraic expression problem. And it is no problem because it was just fun. One more nice long one like that, maybe more than one more. I have a bit of time. But I do want to try evaluating an expression with some exponents in it. Maybe I'll even come back and evaluate this expression. We'll see what I have time to do. Another nice long one. 13a. 13, I'll move further over here this time, make sure I have room. 13a plus 5x squared minus 6 plus 10a minus 6 plus 10a plus 2a minus x squared plus 8 minus 3a plus 4a squared. Do I have room for a bit more? Yes. Plus 1, plus 1, plus 1. We can do anything. We can do anything. We can make up as long an algebraic expression as we want. I went so far, I almost got to the end of the video window on this side. You know what? I'm going to add an a squared over here. How many terms do we have? 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13. 13 term algebraic expression, and I'm going to simplify it by combining like terms. So what do I have here is a squared. That's what I'm starting with. I'm going to cross it out. Let's go a little longer. How many other a squared terms? Oh, I only have this one other one. It's the only other a squared term in this whole thing. So I see x squared, and I make sure I don't get mixed up with that. It's not a squared, it's x squared. And then I see a, but no, that's a. It's not a squared. I have everything that I need for the a squareds. A squared plus 4a squared is equal to 5a squared. And they're both crossed out. Now we have a's. 13a plus 10a. Okay, that's 23a now. Oh, plus another 2a, 25a. Minus 3a. 25a minus 3a is going to give me 22a. And I'm finished with all the a's, so I have plus 22a. Here's an x squared. It's the only, no, it's not. The second there, I thought it was the only x squared term. But no, we have minus x squared here. 5x squared minus x squared is equal to plus 4x squared, and I'll cross those two out. Is everything else a constant term? Yes, it is. Minus 6, starting off with a negative 6, plus 8 is equal to positive 2, plus 1 is 3, plus 1 is 4, plus 1 is 5. Not so bad, plus 5. Cross out all of those. And double check and make sure I didn't miss anything. The more complicated it gets, the more it doesn't get more complicated. That's my take-home message from this lesson. Seems really complicated, but we just pieced together some tools we already have in our toolbox that we've been working on a lot the past couple of weeks, and they all just come in handy. So it is really, it's like having two big toolboxes with all sorts of stuff in it, all this math that we already know, that we're able to just piece together as we need it, and there is all sorts of tools in that toolbox that I didn't need for this particular question, so I just left them in the toolbox and didn't use them. It's cool. The toolbox is cool. And says the guy who likes working with wood. Really likes buying tools. Okay, stop thinking about buying tools right now, Doug. Let's evaluate an algebraic expression that has exponents in it. It won't be quite so long as this one. Have I covered everything on my list? Yes, I have. So that is the end of my lesson plan. I have an algebraic expression, 3x cubed plus 2x squared minus x plus 6. Okay, so there's only one variable, which is x. There are 4 terms, and none of them are like. So I cannot combine any like terms. So if I saw this and no one told me in the instructions what they wanted me to do, I would realize, well, I can't combine like terms, so I cannot simplify this. But I could evaluate this. So if someone just told me what value they wanted for x, I'd be able to do that. How about if x equals 2? We have 3 times 2 cubed plus 2 times 2 squared minus 2 plus 6. So I just keep on replacing every x with a 2 until I've replaced all the x's with a 2 and I don't change anything else. And then I have to obey the order of operations. I cannot multiply this by 3 because there's an exponent. I do exponent before I multiply. 2 cubed is equal to 8. 2 times 2 times 2. So I have 3 times 8. And then that's a multiplication, but I see an exponent over here, so I want to do that first. 2 squared is equal to 4. This 2 is going to be multiplied by a 4. I think I've done enough for one line. I've simplified both exponents. Now I have multiplications that I have to do before I add or subtract. 3 times 8 is 24. 2 times 4 is 8. 24 plus 8 is 32. Minus 2 is 30 plus 6. My answer is 36. That was fun. It is fun. So more complicated algebraic expressions end up not really being more complicated to evaluate. It's complicated to say all that. Let's do the same algebraic expression, but with x equal to 3 instead. So we have 3 times 3 cubed plus 2 times 3 squared minus 3 plus 6. I can do this. 3 cubed. Remember that one? 3 times 3 times 3. That is 27. Use calculator if it's necessary. Plus 2 times 3 squared. 3 squared is 9. Minus 3 plus 6. 3 times 27. Remember that? We saw that before as well. That's 81. Plus 2 times 9, which is 18. Minus 3 plus 6. Now all the terms are like. Hey. Almost didn't notice that. They were not like terms at first. We could not combine any of them. But once I was able to evaluate by making x equal to 3, everything became a number. And all these numbers, none of them has a variable anymore, so they're all like terms. I can combine them. 81 plus 18, that is 99. 99 minus 3 is 96. 96 plus 6 is 102. Yeah, 102, that's the right answer. I did it. And I'm pretty much out of time. This is fun stuff. I think today's lesson had more than one good puzzle book for the bookstore in it. I think the combining like terms was its own cool puzzle book. The simplifying exponents by itself was its own cool puzzle book. And the evaluating expressions was its own cool puzzle book. But then you can take a cool puzzle book that is, let's combine all three of these cool puzzle books into one really big and cool puzzle annual this thick. That'll give us a lot to do while we're riding on that train or plane or whatever it is. And I have a dog who is stretching and trying to look cute because she wants to get my attention because she knows it's supper time. So I'm going to pick her up. I'm going to present her to the camera so that she can hog the view of the camera again. See, we end this lesson the way we started it. Right, Mocha? Right? What's over there, Mocha? What's there? Trying to get her attention, but never mind. It was fun as usual, and I will see you next time. Yeah, here I am, behind the dog. She keeps on getting in the way. Okay, I'll see you next time.